Well, hello, welcome back. I made a earlier video that showed how to solve a two-dimensional collision problem using conservation of momentum, but that one was a situation known as inelastic, where the two objects stuck together after they collided. So this time I wanted to show you an example of an elastic collision where they bounce off each other. And at least in my class, my expectation will be for my students to solve ones where one object is initially at rest. Makes the math a whole lot easier to deal with. You can solve it using as much geometry as you do anything else. So you may find that you've got more advanced problems to solve if you're not in my class. So I'm going to at least show you the principles here. Maybe you can extend it to your situation. So I want to draw a diagram showing what's going on both before and after. And I find that these before-after diagrams are really helpful for just organizing in your mind what's going on. So suppose we have a 12-kilogram object that starts out moving at 7 meters per second, and I'll have it rightward. Now this could really be any orientation. And the other object can be an 8-kilogram object that's just sitting there ready to be struck. So I could even write V initial sub 8 equals 0. I use little subscripts of subscripts a lot of times to show specifically which object I'm referring to. And then a lot of times that problem will describe, that the one object that was moving is now moving at a different angle from how it was. So suppose we say that the 12-kilogram object moves 58 degrees below the direction it started out, or just 58 degrees off of the direction. So what would that look like? If you imagine moving in the same direction will be horizontal on my page. So now we'll have the 12-kilogram object 58 degrees below that. Didn't quite draw that at enough of an angle, but it's close enough. So that vector there will represent its final velocity. So we'll call that VF12. And we'll have the 8-kilogram object moving at a right angle to that. This is not actually realistic. I'm doing this only for the sake of for using momentum. If you've studied elastic collisions, you will know that, well, you could figure out that the numbers that I've chosen here don't actually work out quite right. But it can still be solved using conservation of momentum. We're going to ignore the energy aspect. You may not even be to that part of your physics class yet, but you'll see later why this can't work out. So we'll call this VF8, and that is 32 degrees. I'm choosing 32 because 32 and 58 together would make 90 degrees with these relative to each other. Again, I didn't quite draw this as enough downward. It doesn't look like a right angle, but it's enough that we can solve this. So how do we go about solving a problem like this? Well, we still use the general concept that the total momentum before has to be equal to the total momentum after. But when we arrange this, we can't just put it in a nice little simple algebra equation, because that can't account for the directions. So we could make a momentum table out of this and show, in graphical form what all of these momentum numbers are. And so that shouldn't take us too long. I'm going to make it a little quick here. So I'll have one line for my 12, one line for my 8, and each one I'm going to account for its momentum both before and after, and then I'm going to have a total here. So the 12 kilogram object is the only one with any momentum before, so I can put a 0 in for the 8, and this one has 84 units of momentum, but I'm going to show this with an arrow. That's a vector arrow showing rightward momentum. So my total is 84 rightward. So that means if I'm starting with 84 rightward, I have to end with 84 rightward. But how is that going to be divided up? I know some of it, the 12, is going 58 degrees below, and I know that the 8 ends up 32 degrees above, but I don't know what those numbers are. So how would we figure out what those numbers are? Again, it's not just to throw it in your calculator or write a simple equation from algebra. This solution is going to come from a diagram showing that these two vectors, these momentum vectors, have to add up to this one momentum vector. Remember, I'm drawing a momentum table. I'm not just drawing a velocity table. There's no such thing as the conservation of velocity. So how do I show that these two vectors have to sum up to be 84 rightward? Well, you use vector addition. Vector addition says if I arrange these two head to tail with each other, that they have to be equal to this one resultant that is rightward. So it's kind of like knowing the answer and figuring out the two parts. You know, you've done this in math before. So I'm going to draw the 58 downward like this. That'll be my momentum for the 12. And I'll put a little 58 degrees there just to remind myself that's there. And then I'm going to add to it head to tail the 32 degrees above horizontal vector. So I got to go here to where I ended my first vector, and I'm going to peel off at 32 degrees. So that's why I'm choosing that direction. And then here's the quandary students usually run into. They say, well, how big should I draw it? I don't even know what that number is. But you have to know what this has to end up equaling. When I'm all done, I have to have a resultant vector going from the tail of the first vector to the head of the last vector. So my final momentum has to end up over here somewhere, rightward. So I'm going to draw this momentum for the 8 kilogram ball so that it ends up exactly to the right of where I started my initial final momentum vector. So this is P8, pointed up at 32 degrees, and here was my initial momentum. That's the 84. All right, so I've got a vector equation here. The final momentum of 12 plus the final momentum of 8, when added together, gives me the initial momentum that I had in my system. I have a right angle down here, so I'm just going to solve a right triangle problem. And I'm not going to do all the math to solve a right triangle problem. This is using sines and cosines, along with this here, which is the hypotenuse. I'm going to use, one of these angles. I can use the 58. I could even use the 32, which shows up over here. But I've done this earlier, so I know what this math is going to come out to be. The momentum here has to be 84 times the cosine of 58, which would be 44.5. That's momentum. Now that's not velocity. And then the other side is going to be 84 times the sine of 58. And that's going to be 71.2. So now that I know each object's final momentum, I can just divide by each individual mass. And I'll just show it here. The momentum of number 8 divided by the mass of that number 8 gives us about 8.9 meters per second for that one. And if we divide 44.5 by 12, we're going to get about 3.7 meters per second. For that one. So there's our final numbers. Again, there's no shortcut to getting that. It's drawing the triangle and then getting each momentum vector afterwards, and then the final step is just to divide by the mass. So pretty much a standard kind of a situation. You'll have to customize it for whatever your problem is, but hopefully that gives you a good start. All right, good luck.